I guess I was asked to talk, I guess, maybe I should be a little bit more conservative. Autumn actually didn't say that, but my interpretation of what she was asking was talk about something that electrical engineers do, and that computer scientists might find interesting. And I realized there's no intersection. So basically, I'm just going to talk about feedback and information theory. Hopefully, you'll find it interesting. So we know that feedback is, useful in many cases, sometimes not, but so in real life. But let me try to convince you that it's also interesting and useful for other problems that arise from information theory. And for that purpose, let me first start by introducing the simplest setting that an electrical engineer or information theorist might be interested in, which is the communication problem. So this is the simplest instance of the communication problem. It's a point-to-point communication problem. There is a transmitter here and a receiver on the other end, and they try to communicate through a noisy channel. So there is a channel, and it is characterized by some sort of a conditional distribution, P of y given x. So y is the output to the channel, and x is the input. So given that you put x into the channel, then you see the distribution P of y given x to the output. And in the simplest setup, we're assuming that this channel is memoryless. So that means that whenever the transmitter uses the channel in different time instances, these instances are independent. And let's assume that the transmitter can use the channel n times, n independent times. And the goal of the transmitter is to send, during that time, some number of bits through the channel. Let's say n times r. Okay, so if the channel is used every second, then this would mean the rate of r bits per second has been conveyed over the channel, and you want to do it reliably. Okay, so we'll define what reliable means in a sec. Slightly more generally, or more accurately, the transmitter has some message W, which is one of 2 to the nr possible messages representing nr bits. And he takes that message and needs to create some input to the channel at time k, xk, which is a function of the message. So this is a coding scheme. It's some sort of a code that takes the message and connects it to the channel. And then at the output, yk is observed, a random version of xk. And the receiver collects all those yks, 1 to n, and outputs some w hat, which is an estimate of the message that was transmitted. Hopefully, it's the correct one. So there's going to be some error probability in general. If it helps, you can think, and it will be helpful in some cases as we continue, to think of this the simplest channel that one might consider, which is the binary symmetric channel. So in this case, the input to the channel is a bit, the output is also a bit, and the output is a flipped version of the input with probability p, and retains the input value with probability 1 minus p. So this is one example of a channel, but these channels could be general, could be continuous input, continuous output, and so on. So one can define some concept called, or notion called capacity, which is the highest possible rate R, such that the error probability can be driven to 0 as n goes to infinity. It's not clear this quantity is even positive, but it turns out that it is. And a famous result by Shannon from 48 says that there is indeed a sharp threshold. There is a positive threshold called capacity, below which you could communicate, above which you cannot communicate reliably. And not only that, this quantity has a very simple formula. It's supremum over all input distributions, P of x, of this quantity, which is a mutual information, called a mutual information between the input and the output, and has this very simple expression, the expectation of the logarithm of a ratio of the joint distribution, Pxy, to the product of the marginals. So this is an easily computable quantity, and it characterizes what can be done over this channel reliably. And some people have also been interested in the behavior of the error probability for different rates. So it turns out the error probability can drive the error probability exponentially fast to 0. And this ER is the reliability, so-called the reliability function of the channel, characterizes how fast that can happen at any possible rate. And a lot of works on that. This is less well understood. There's another notion of capacity I just want to mention because I'm going to just use it as an example in a sec, which is a zero error capacity, also introduced by Shannon. And this is the same supremum over rates, but this time you want the error probability to be exactly 0, not vanishing, but exactly 0. And this is a combinatorial creature. It's much more difficult to handle. And in general, there is no known formula for it. Okay, so here comes feedback into the picture. Can feedback help? This is a question that you might want to ask yourself. So we have a communication from point A to point B. Maybe there is some backwards link. Can it help me achieve my task? So here is the most clean, I guess, setup for feedback. Again, there's a channel PY given X from transmitter to receiver. And let's assume, this is a very unreasonable assumption in many cases, but still interesting to study, that there is an instantaneous noiseless feedback back from the receiver back to the transmitter. So the transmitter at every time point K knows the entire received sequence. Okay, so this is called noiseless feedback. And the question you might ask is what happens to capacity or reliability if you have access to such feedback? And here, I guess there are two, colliding intuitions. One would say, okay, so the transmitter knows everything that's going on in the receiver. It can help push information faster because it knows what's going on. It doesn't have to guess anything. On the other hand, the channel is memoryless, right? So you cannot predict what it's going to do. There's maybe no gain in actually knowing what happened before. So it's maybe not clear what exactly is going on. So here's one answer. If the channel is memoryless and we want the vanishing error probability, then it is already observed by Shannon in 56 that feedback cannot increase capacity. So it doesn't help you in terms of increasing your rates. More than that, it cannot even improve your reliability in many cases. Okay, so for a large class of symmetric channels, you cannot get a better behavior of error probability. This is conjectured to be true in general, but not proved. You could improve your reliability, your error probability significantly if you kind of tweak the setup and allow for a random decision time. This was observed in 72 by Burnashev, was characterized exactly. But this is a little bit of a hack because what you're doing is essentially saying, okay, there's some error probability if I stop at time n, but if I can use the feedback to sort of gauge this error probability and maybe continue to transmit a little bit more until it drops a little more. So I'm sort of trading off error probability with a little bit of time. So it's not exactly fair. Well, you might say, okay, I knew it, right? Channel is memoryless. Of course, there's no way to gain. But then test your intuition. This time it's zero error, okay? So this is the same memoryless channel. You cannot predict what it's going to do, right? But the error probability needs to be exactly zero. In this case, again, Shannon showed that feedback can indeed increase capacity. Okay, so you can actually, the fact that you know what happened in the receiver actually can help you, and it can help you significantly. In some cases, capacity can be zero without feedback and can be arbitrarily large with feedback. In this case, there is actually a closed form solution for how the feedback capacity is zero, feedback capacity looks like. And there are a bunch of other things which we're not going to focus on, but just going to mention that people have worked on effective feedback in various setups, so it can increase something called the erasures only capacity if you allow only for erasures. So you don't allow errors, but you allow the decoder to say, I don't know. So that type of capacity is also increased by feedback. Adversarial channels, if there's no statistical model, but there is an adversary that is allowed to mess up your channel in some sense, some limited sense, then that could also help. Feedback can also help. Channels with memory, of course, you can predict what the channel is going to do, so that is kind of obvious that would help. And in some cases, you can even attain something called the empirical capacity, where there is no capacity, where the channel is actually anything. There is some guy who's messing up your channel in any arbitrary way. There is no way to guarantee any rate, but you could use feedback to actually communicate at the rate that corresponds to how well this guy was actually messing up your communication. And of course, multi-user channels as well. That could be feedback could be useful. But let's go back to memoryless channel, the most basic model. We just said that feedback doesn't help you, right? I mean, it doesn't increase capacity, it doesn't increase reliability, more or less. But maybe you're not satisfied yet. So achieving capacity without feedback, so we don't need feedback, right? So we can achieve it without feedback, is very far from trivial in general. Okay, so constructing a good error-correcting code for a general channel that operates close to capacity is an onerous task. I mean, decoding it is very difficult, designing it is very difficult. We don't always know how to do it. So one question you might ask yourself, and maybe it's not clear at that point why that makes sense, is can feedback help in terms of complexity? and I'm using complexity here loosely. I know it's a CS forum, so can you create or build a scheme that is very simple to analyze, very simple to decode, that uses feedback? And we'll see what that means in a minute. Okay, so in order to make this connection, I need to sort of digress a little bit and talk about how feedback is related to search problems. Okay, and that will sort of mesh together well in a few slides, I hope. So let me discuss a search problem and then see how it's related to communication with feedback. So here is the search problem. It's sort of a very generic search problem. There is a target W. It's W, it's not by mistake. It's the same. It's going to be the message in a minute, but right now it's a target W that is placed on a unit interval, let's say, arbitrarily or uniformly at random or whatever you want. And there is some agent that is looking for that target. And the agent can query the interval, can make n binary queries. They can be not non-binary as well, but let's keep them binary. Basically can ask, is the target in this subset? Yes or no? Okay, so this subset is denoted here by sk. At time k, it can ask this question. So in this case, if that is a subset, the answer would be yes. In this case, the answer would be no. Subset doesn't need to be an interval, of course, but it's a little difficult to draw something less that is not an interval. So of course, if that's the whole thing, then it's not very interesting. But the crux of the matter is that unfortunately, that agent is getting noisy answers. So the agent wants to know if the target is in a certain interval, but that answer, yes or no, goes through some channel, py given x, and you can think of this as being a binary symmetric channel for the purpose of this talk. So basically, he's asking, is the target in this subset? And the answer is flipped with probability p, okay? And yk is what the agent actually observes. And we can say that the agent acquires the target with target and rate rho if it can locate it up to resolution 2 to the minus n rho. Okay, so it can pinpoint it up to resolution 2 to the minus n rho while making sure the error probability of that detection goes to 0. Okay, that would be the definition of targeting rate. And we could also define targeting capacity, which would be the maximal possible targeting rate for this setup. So here's the noiseless case. That's going to be easy, right? So noiseless case, the agent is actually getting whatever he's asking is getting the answer noiselessly. Okay, so is it in this set, yes or no? Okay, there's no noise. And in this case, I guess most people would say, hey, I would do a binary search, right? This is the most reasonable thing to think about. And I'm just note that this is an adaptive strategy. So what do? You basically ask, is the target between 0 and half or not? If the answer is yes, you just narrow it to 0 and half, divide it in 2, and so on and so forth. And it's very easy to see that after n questions, you can locate the target to within 2 to the minus n resolution with no error. And your targeting rate is 1, and this is actually a capacity. You cannot do better than that. You can actually do that without adaptiveness, right? You could just think of this W as, think of the binary expansion of W and just ask questions that correspond to the first bit, the second bit, and so on. And these questions are not going to be intervals. So the first one is going to be an interval, then it's going to be union of 2 intervals, and then union of 4 intervals, and so on and so forth. But it's essentially the same thing, just running things in parallel, basically. And you can get the same targeting rate. Okay, so that's easy. What happens with noise? Okay. So in order to answer the question, we actually know the answer already, more or less. It's related to what we've discussed. Let's see how. In order to answer this, we need to see there is an analogy, or actually an equivalence, between searching with noise and communication over a noisy channel. Okay, this is actually the same problem. And this was observed back in '74 by Bornashev and Zigangirov. And the analogy goes like this. You can think of the observation channel the agent is looking through as a communication channel. Think of the target as being the message. The location of the target, at least the bits, think about the bits, W1 to W whatever, as being the bits you want to transmit. The agent is playing the role of both transmitter and receiver. So basically it's asking the question, which is producing xk, the input to the channel, and observing the answer, yk, which is the output of the channel. Right? The only subtlety here is that the agent doesn't know the message. Right? It's not a real transmitter. It doesn't know the location of the target. Otherwise, everything would have been trivial. But it can actually evaluate the input to the channel, even though it doesn't know the message. Okay, this is a little subtlety. And then if you realize that, then the targeting rate is basically exactly the same definition, up to some small subtleties, as a communication rate. And then there is the analogy between adaptive search and non-adaptive search. What does that mean? Adaptive search means you're using feedback, right? Why are you using feedback? Because your next question as an agent depends on all the answers you've seen so far, which are the whys, right? The outputs of the channel, right? So how is the transmitter? How can the transmitter know what to ask, or what to send to the channel if it doesn't know the why case? It has to know it, so that means that you have feedback. Non-adaptive search is communication without feedback. You set your sequence of questions or sequence of queries in advance, and that's it. Okay, so these are the two cases that correspond to either feedback or no feedback. And once you realize that, then we know already that feedback doesn't help capacity, right? So if feedback doesn't increase capacity, then also in a search problem, adaptiveness is not going to help you. Okay, it's not going to help you in terms of targeting rate. You're going to get the same targeting rate with whatever you do, whether it's adaptive or non-adaptive. So the targeting capacity is exactly the Shannon capacity of the channel, of the observation channel. It is not increased by feedback. It's not increased by adaptiveness. In order to achieve this, if you're the agent, and I just told you that, you don't need feedback. In order to achieve this, you need to use error correcting codes, basically. You need to use a communication scheme. This is quite annoying. If you think about this as a search problem, this is quite annoying. It's very difficult to construct and to decode. Also, the intervals you're asking are going to be a union of a gazillion intervals. It's not elegant in some sense, right? It's optimal, okay, at least in the terms of capacity. But it's not elegant. And at this point, you might wonder, what is the analog of the noisy counterpart of this simple bisection algorithm, right? The binary search, right? Why don't we perform something that is more closely resembling a binary search? So here's the answer. This is called the Horstein Scheme back in 1963. You can think of, let's think of the message or the target, I'm going to use this interchangeably now, as being uniform over the unit interval. Okay, so here is its PDF. It's a uniform PDF. And again, we're assuming a binary symmetric channel. So our answers to the queries are flipped with probability P. What would be our first query? Of course, you could ask the same question you would ask without noise, right? Ask whether the target is to the left or to the right of half, right? And you get some answer. Now, after getting this answer, you can update your PDF, right? And it will look like this, maybe if you got a right answer, right? Because now the region between 0 and 1/2 is more probable than the region between 1/2 and 1. But before, if there was no noise, then this would have been the whole probability space, right? This would have been 0. Okay, but now you can't just throw it out because maybe there was an error. So before, you would just take this region between 0 and 1/2 and cut it in two pieces, right? So what would you do now? Just take the posterior distribution, compute the median of this distribution, and put the line here in the median, right? So you have probability half here and probability half to be here, regardless of this shape. And that's your next query. Your next query is going to be, is the message or the target left or right of the current posterior median? That would be a natural analog of the binary search. And you can go on like that. Compute the posterior, find a median, ask the question, and continue like that. Hopefully, after a lot of, after n questions, maybe n is large, you get some concentration, hopefully, around the true message point or the true target, so you can locate it. Okay, that is not guaranteed maybe, but you have to prove that this happens, but this is what you would hope. And this is what Horstein, back in '63, conjectured. And he not only conjectured that this happens, there is some concentration, he also conjectured this is an optimal concentration, that the width of this shape is roughly 2 to the minus n capacity. So that means you can locate the target with resolution that corresponds to the channel capacity, which is the optimal thing that you could, the best you could hope for. And he gave some hand-waving arguments to convince, but remained open for a while. We'll discuss this in a sec. Let me just mention another scheme. I'm not going to discuss it, but 3 years later, people came up with a different scheme for the Gaussian channel. It's a more rich channel. The input is a real number. Then there is some Gaussian noise added to it to obtain the output. And there's noiseless feedback. And it turns out that you could come up with a very simple recursive linear estimation scheme that attains the capacity of this channel. Basically what the transmitter is doing, it's computing the estimate that the receiver has of the location of the target or of the message and sending the error term. Okay, just taking the difference and sending the error term multiplied by some number. And this achieves capacity. Now, these were basically the two schemes that were out there that were simple. One of them was conjecture to achieve capacity, the other one achieved capacity, and that's it. Fast forward 40 years, we were actually looking at trying to prove the Horstein conjecture. And we actually realized that there is one unifying principle that connects those two schemes and actually gives you a scheme that operates for any memoryless channel. And this was termed the Posterior Matching scheme. And the idea is very simple. This is what you send or ask at the k+1 instance. All these capital Fs are CDFs, cumulative distribution functions. What you do is you apply the posterior CDF of the message or the target, given what you've seen so far through the feedback, to the message and that sequence of observations. Now, if you apply a CDF to a random variable, to its own, to the CDF of a random variable to itself, then you get a uniform distribution. Not only this is uniform, but since this is uniform for every choice of yk, it is also independent of yk. So you've got something that has a fixed distribution. It's independent of what you've observed as a receiver or as an agent so far. And that's basically what you're missing in order to obtain the location of the target or the message. What you do is with this quantity, it's a continuous quantity. You have to match it to the channel. What does that mean? If your channel is binary, you can't send a real number through it. So for instance, if x is Bernoulli half, then this inverse CDF is just a quantizer above and below half. So basically what this says is take the posterior and send a 0 if you're below the median, 1 if you're above the median, which is exactly the Horstein scheme. But this is general. This works for any channel. The nice thing about this is that there is a recursive encoding for it. So you can actually break down this big formula and come up with a very simple recursive structure. So basically you have this state variable W, which is sort of an adapted message, and you keep applying this function to it depending on what you observe, and that is very simple and keeps going like that. And there's also recursive decoding. It's a very simple scheme to encode and decode. Of course, the nice thing is that it's not only simple and sort of elegant, it's also optimal. Okay, so this structure of recursiveness allows you to analyze the contraction properties of this basically a Markov chain over CDF space, and using that you could show that this actually achieves capacity. So this resolves the Horstein conjecture in a strong sense, actually gives you a scheme that is optimal for essentially any memoryless channel. And other things have been studied about this, but I'm not going to discuss. How much time do I have? Like 5 minutes. Okay, good. All right, so we've sort of made a full circle in a sense that we began by saying, okay, feedback doesn't help you, but maybe it can help you with complexity, connected it to search problems, and through the search lens, we're able to come up with a scheme that is optimal, achieves capacity in a very simple way. And as a search algorithm, this is really nice, because in search problems, the feedback is inherent. The noiseless feedback is inherent. There's no channel. You just get the answer, right? But in communications, nobody's going to buy anything from you if you say, "Oh, I have this great system that works. If only I had noiseless feedback." But that's not gonna do it. It's a non-starter. So it doesn't make sense to assume that the forward channel is noisy, but the feedback channel is like completely clean. So can we do something when the feedback channel is noisy as well? So here is a discouraging conjecture. It says that basically any finite dimensional recursive scheme that is reasonable somehow, in the sense that is time invariant, continuous, and so on, cannot achieve any positive rate. It will just break down. Okay, so basically it says if you're looking for a posterior matching scheme of the type that I just showed you with noisy feedback, forget about it. That's discouraging. And this actually has been proved for linear schemes over Gaussian channels, but in general, it's still still open, but it would be very surprising if it's not true. So if this conjecture is true, so what is left to do? I mean, if you want to take these nice recursive schemes that operate with noiseless feedback and actually use them for communications with noisy feedback, can you do it? Or it seems like you cannot. Well, it turns out that not all is lost in some sense, because we discussed, we define capacity as something that you achieve when you need air probability to go to 0 as n goes to infinity. Nobody cares about that for real, okay? In reality, if you go to an engineer and ask them what they care about, they want low air probability, moderate block lengths, moderate complexity. That's what they want. They don't care about asymptotics. The asymptotics is nice and it's a benchmark, but nobody really cares about it in reality. So the goal would be not to maybe achieve any rate with arbitrary low air probability, but to actually come up with a simple recursive schemes of the nature that we discussed that would just work well, okay? Would be close to capacity, it would have a nice, reasonable error probability, let's say 10 to the minus 8, whatever, okay? Something that everybody is happy with, and it would be simple, okay? Simple to encode, simple to decode. Now, the bad news is that if you take posterior matching, the recursive scheme I showed you, and apply it with noisy feedback, it just breaks down completely. So any little amount of noise in the feedback has this sort of a butterfly effect that accumulates to the closed loop, and everything just goes to hell. So we don't have any cure for this, but you can actually dampen the effect. So sort of delay the end of life. And you can do that, at least for now, that all we know that we can do it for Gaussian channels. So if you have a Gaussian channel, Gaussian forward channel, Gaussian feedback channel, and remember that linear schemes fail, okay? They fail miserably. But it turns out if you replace arithmetic, linear additions and multiplications and so on with modular arithmetic, then you can actually get a scheme that works pretty well. So what happens, it doesn't break down immediately. The error probability goes down, and then goes down significantly enough, and then before it starts getting out of control, you just stop and start over. Okay, so it actually becomes a practical scheme. And in some situations, I'm not going to discuss the details, but if the feedback link is sufficiently non-noisy, if it's not horribly noisy, then it can sometimes beat state-of-the-art codes. It can achieve even better rates than what you achieve with reasonable codes that people use today that don't use feedback. And in terms of complexity, it has something like 2 orders of magnitude reduction in complexity. So now this completes the tour, and we've seen what feedback can do for you in search, and now we can see that feedback can also help you maybe in a real life problem. And I think I'm not going to bore you with concluding remarks. I think I'm out of time. So thank you. Sure.
In the CS world, we have something called noisy binary search.
Yes.
Do you know this?
I think it's probably the same.
No, it isn't.
It isn't. Okay, so what is it?
Basically, you go according to the answer that you got, but you might find yourself in a state that you realize is inconsistent, and then you backtrack.
But what defines consistency?
So you might ask like both sides and say, oh, it's not here and it's not here, so I have to go back one step.
But there's no error there, right? I mean, so if there is an error, then you could get this kind of answer and it's still valid, right?
Right. But eventually, with enough repetitions, you'll get the right answer.
Right, but that would work probably very far from capacity. I mean, if you do repetition coding like that, of course you could zoom in on your point or your message or whatever you want, or the target. But I think your rate is going to be very, very poor. I mean.
So at least in terms of a binary search, it's still order log n.
Order.
And there's no prior. And there's no prior.
But we care about the constant before the order, right? So the constant is basically the capacity, right? So you could get like order log n with non-optimal constant. I'm sure different ways. But I think this is maybe there are other ways to do it, but this is the way that I know to get like the correct constant. So interesting to see if. I don't know where you apply this, but we're interested to see if these kind of things could be applied somehow.
As usual, let's take it off.
There you go. Thanks.
Welcome.